today. So we're starting with this material and we call it F-test versus nested F-test. In statistical analysis, where we're looking into building relationship or characterizing relationship between variables, we normally make use of F-tests. We make use of nested F-tests. So what we want to do today is when is F-test appropriate and when is nested F-test appropriate. So I'm also going to say nested F-test is the same thing as partial F-test. Please take notes. Okay. Now in the outline, F-test versus partial F-test. Okay. Now I want to first start with the F-test. Now, what we use F-test to do, we use F-test to compare an intercept model, okay, and a regression model. Okay, take a look at what I'm displaying now. I want to work on an example where we are into factory production, and of course, we want to characterize relationship between run size and run time, and of course, if we are testing this against this, give me 1 second. If you are testing, I need you to look at the hypothesis right now. If you take a look at the non and the alternative hypothesis, okay, when beta 1 equal to 0, when slope is 0, okay, that is an intercept model. Okay, intercept model, you know what this guy actually mean here? What that guy mean is that run time is not related to anything. Does that make sense? That is a non-hypothesis. But take a look at the alternative. The alternative hypothesis is trying to say, you know what? The slope is significantly different from 0. Okay, beta 1 not equal to 0 actually means relationship exists. Okay, and that's a full model. Okay, so we normally make use of F-test when you are testing between an intercept model and a full model. Does that make sense right now? And of course, you remember the other time, the formula, the F statistic, you remember we did this in this class the other time, when we're doing the composition of response variable, where we're able to decompose, the total variations around the response into what we call explain and unexplained variation. And of course, if you can see right now, the F-test statistic is sum of square reg. The sum of square reg is explained variation divided by 1. Why are we dividing by 1? That's a degree of freedom for regression because we got two parameters, right? Degree of freedom is going to be 1. Then divided by RSS. The RSS means residual sum squared, which we also call unexplained variation. So n minus 2 is going to be the degree of freedom for error. Okay, and of course, I'm going to show you something right now really quick, the output. You know, some of you may be wondering, when I generate an output, when I run a regression output, I got this guy for simple linear regression. Okay, what is the difference between a t-test and f-test? For simple linear regression, okay, if you are conducting an hypothesis on significance of the slope, you make use of this p-value, right? That's for t-test, right? But for the f-test, it is this guy and this p-value. But I wanted to take note of something now. For simple linear regression, I'm going to say that again. For simple linear regression, the p-value for f-test is also going to be the same as the p-value for t-test. Do you see that? And that was why I said they are equivalent. Can you take a look at this and this? They are the same. For simple linear regression, the p-value, okay, associated with the slope when you are conducting a t-test, it's all going to be the same as a p-value when you are conducting an f-test. But do you know what will be different? Please pay attention. A lot of me time two question here. What is going to be different is this. Do you see T value here? And do you see F value here, right? Are they the same? No. But we have the same P value. They got the same P value, but they're going to have the same statistic value. But let me tell you this. They got relationship. They got mathematical relationship. Do you know what mathematical relationship is? When I square T value, it's going to give me F. Can somebody square 6.98? Exactly. Exactly. That is a mathematical relationship. Okay. The test statistic value for T is not going to be the same as that of the F, but they're going to have the same p-value for simple linear regression. Okay. But they do the same job. Okay. They are actually testing, they're all comparing intercept model with a full model. Does that make sense now? Okay. Now, please, I need you to pay attention. You know, right now, we're only talking about t-test and f-test. We've not talked about partial f-test, right? This is just t-test and f-test. Okay. But take a look at this. I want to go into another data now, rate my professor data set, and we want to consider three variables. Okay, quality, easiness, and pepper. Okay, quality is a response variable. The other two are independent variable. They are explanatory variables. But you know, one of the explanatory variable here is categorical, which is pepper. Okay, please take a look at this. This guy here, that's a categorical. A professor may be hot or not. That's categorical, right? Then this is like we're having a combination of a categorical predictor with a quantitative predictor. And what you're seeing right now is the scatter plot. Okay, we can actually plot a variable against two variables at the same time. The scatter plot you've seen before is when you plot one variable against one. But right now, we got more than one independent variable. And that's why you're seeing what you're seeing right now. Take a look at that. Okay? And whenever we have a categorical variable, when you plot a categorical variable, you actually need to indicate, or you need to distinguish by color, you know, so that you can be able to tell the world that color is for no, and the other color is for that. Does that make sense right now? Now, I need you to pay attention now. I'm coming somewhere now. Okay? I need you to pay attention now. Where do we use f-test? We use f-test when we compare an intercept model with a full model, right? You know, if you take a look at this, one here, we are comparing intercept model and a full model. A full model here is a simple linear regression having just one explanatory variable. We can also have situation whereby we're comparing intercept model with a full model, and that very full model has more than one explanatory variable, which is what we want to do here. Please pay attention. You don't understand that question? You know what I want to do here right now? Oh my God. If you take a look at what I want to do now, okay, I'm looking, I have two explanatory variables, x1 and x2, okay? And my intercept model for that situation, give me 1 second, my intercept model is going to be this. You know what intercept model is going to say? The beta 1, the beta 2, the beta 3, they're all going to be 0. Oh my God. Why do I have, you know, that numbers of beta? I'm actually going to tell you right now. Please pay attention. Do you know that the complicated model that I want to talk about is this guy? Do you see the full model? In this full model, I have easiness, I got pepper, and I have the interaction of easiness and pepper. This is the first time in this class that I'm actually going to talk about interaction effects. I needed to pay attention to this guy. Please pay attention. Do you see this guy? What do you see? Multiplying two variables. That's an interaction effect. Okay. Why do we consider interaction effect? I'm going to tell you now. Okay. You know, when you only focus on this, when you focus on this effect, we actually call that main effect. Main effect. Main effect. Please write it down. I need you to pay attention. Please take notes. Okay. When I'm testing effects of a variable separately, we call that main effect. Does that make sense? We can also test the interaction effects. Right here now, right here now, right here now. This is an interaction effect. Interaction. Please take notes. If you don't understand, ask question. Okay. Now we believe in this model. Okay. Our full model here is not just multiple linear regression with main effect. It also includes interaction effects. Now, what is the significance of interaction effect in a model? Please pay attention. Okay. You know, the significance of interaction effect is this. If the effect of easiness, please pay attention. If the effect of easiness on quality is not consistent, because effect of easiness on quality may depend on whether a professor is hot or not. I'm going to say that again. We consider interaction effects when we realize inconsistency in the effect of the main effect. And how can we have an inconsistency when if the effect of easiness on quality depends on PPS? Then we need an interaction effect in a model. So statistically speaking now, if I have two explanatory variables, if the effect of one explanatory variable on the response depend on another explanatory variable, then we need interaction effects. Have I made myself clear, right? Do you need any clarification on that? Okay, so that is the reason why in this model, in the full model, we are considering both main effect and the interaction effect. And that is the reason why the numbers of slopes in this model is beta 1, beta 2, beta 3. The beta 1 is the slope for easiness. The beta 2 is that of the PPS, and the beta 3 is for the interaction. Because we can test the significance of the beta 3. If beta 3 is significant, then we're actually going to say interaction effect is justified. We don't just do what we do. We have reason, for doing what we do. Does that make sense? Now, that is the reason why in the intercept model, we know what we're trying to say. We're trying to say the beta 1, the beta 2, the beta 3, all equal to 0. All equal to 0 means quality does not depend on the main effect of easiness. Quality does not depend on the main effect of PPS, and quality does not depend on the interaction. Does that make sense? That's what we mean. Okay. Now, please pay attention. You see, this is our hypothesis that we're actually testing. Okay. Now, the test statistic is going to change. Oh my God. I need you to pay attention. Can I walk you back a little bit? Let's see the F statistic when we're dealing with the simple. Oh, the F statistic, we have sum of square root divided by 1, right? Where's the 1 coming from? That is the degree of freedom for having two parameters in a simple linear regression model, 2 minus 1. That's going to be 1, right? Then RSS n minus 2. N minus 2. Where is it 2? What is the meaning of that 2? That 2 is the number of regression parameters, okay, in a full model. Now, let us see how it's going to change here now. We're going to see how it's going to change now. Let's see how, oh my God. Look at this now. Where is the 3 coming from? Because in the full model, how many parameters do we have in the full model? 4. Beta naught, beta 1, beta 2, beta 3, making 4. 4 minus 1, then 3. Any question? Whether any person online? Or those of you online, can you see? Can you confirm? Are you still hearing me clearly? Okay,
Yeah,
make
we're
sure you.
hearing you.
Oh, thank you so much. Make sure you ask question too. Okay, ask question if you don't understand. You are allowed to talk. As far as I'm concerned, there is no question that is stupid to me. No question. Okay. Now, n minus 4. Where's the 4 coming from? That would be the numbers of parameters. Does that make sense? You can see, depending on your full model, depending on the numbers of parameters in your full model, we expect the F statistic formula to change. And what is going to be changing now? What's going to be changing is going to be the degree of freedom for regression and the degree of freedom for error. That's what is going to be changing. Okay, now when we have something like this, can we have an arrow code for it? Okay, let's have an arrow code now. Oh my God. Look at that. This is the arrow code whenever I actually, want to test both the main effect and the interaction effect. It's just going to be 1 plus the first variable, the second variable, then multiplying them. Okay, it's less than that. And at the end of the day, we're having this result. When you do summary, can you see the result right now? This is the results. But I wanted to pay attention to this result. Please pay attention. I want to say something about this result. Okay. Now here in this result, take a look at this guy. Okay. Don't forget the paper is categorical. Okay. We have yes, we have no. Okay. What is arrow telling me? Arrow is trying to say, oh, I've labeled yes as 1 and I labeled no as 0. Does that make sense? The categorical level that is not showing in the regression output, okay, that has been coded automatically as 0 by R. The one that is showing, is what R coded as 1. Do you want me to repeat that or you grab that? You all grab that, right? I told you when you don't hear me clearly, please ask question. You pay for the service. Okay, now do you see this guy? That is the interaction, right? In the interaction, arrow is also going to display that yes. Does that make sense? Now, if I now ask you to write a feeder model, okay, of course you need this, right? Okay, don't forget, you want to write a feeder model now, it's going to be Y cap, okay? Your Y cap is going to be beta naught cap, okay? The beta naught cap, okay, plus the beta 1, cap, X1, okay? The beta 2, cap, okay, X2, okay? Finally, the beta 3 cap, okay, X1 and X2, X1 and X2. This is a mathematical model. Now, the beta naught, this guy is this guy here. Okay, the beta 1 is this guy here. The beta 2 is this guy here. The beta 3 is this guy here. Does that make sense now? That's how to write the feeder model. Imagine I gave you, asked you to do this in an exam and I say, okay, write the feeder model. Okay, that is the feeder model. Okay, I'm gonna move right now. Oh my God, how do we interpret? Let me tell you what is the essence of running an analysis. Okay, the essence of running an analysis because you want to provide a practical answer to a research question, right? It's a research question. A research question we actually translate into research hypothesis. And at the end of the day, you do your analysis, you are expected to make an interpretation. Okay, so let's make an interpretation now. Okay, please pay attention. In the assignment, the assignment 3 has something that has to do with this, where you have a linear regression with interaction. How do you interpret coefficient associated with interaction, or situation where one of the variables is categorical? Pay attention now. Okay, now if I want to, of course, I said a small p-value. Whenever you have a small p-value, that will lead to rejection, right? Will lead to the rejection of what? What do you have in the non-hypothesis? What you have in the non-hypothesis is actually intercept model, okay? And you have a complicated model in the alternative, okay? And that is a technical way, okay? We believe that when the p-value is very small, okay, the non-hypothesis that support intercept model will be rejected. Okay, and your conclusion will be based on a full model. What you're trying to tell the world in that situation is that the full model fits your data significantly better than the intercept model. That's exactly what you mean. And of course, in the context, what are you talking about? Oh my God, the technical way is when I'm just speaking statistics. I'm speaking statistics here. Somebody in psychology or somebody in sociology or somebody in a field that is different from statistics may not understand that technical interpretation. And that is the reason why we need to come back to the context. What are we trying to do? We're trying to look at the relationship between quality and some variables. Now, in the actual sense, what we mean, a linear association between an instructor quality rating and his or her easiness rating of physical attractiveness. That's what we mean. Okay, that's exactly what we mean. Okay, now, see, going back to this now. I want to say something. Pay attention. Okay, you remember the other time when I was focusing on just simple linear regression, I said the p-value here has to be equal to the p-value associated with one of the slope or with a particular slope. Okay, that may not happen for situation where you have more than one explanatory variable. But this is where I'm driving at. When do I use this? That is when I'm conducting a t-test individually, when I'm looking at it individually. Like I want to see what is the significance of intercept? I use a p-value. That's a t-test. What is the significance of easiness? I look at the p-value. What is the significance of period? I look at that. What is the significance of interaction? I look at the p-value. That is a t-test. When you are looking at it individually, that's a t-test. But you know what we want to do now? Please pay attention. Please pay attention. Okay. This guy, that is the value that we got when you make use of this guy. Arrow has automatically given you the value. That is for F statistic. Okay. Now, what is the p-value associated with that? The p-value associated with this is this guy here. There's a connection. Does that make sense to everyone? What is happening right now? Should we reject H0 or fail to reject? We should. Which means because of that, we're using this guy. Not the p-value in the table. The p-value right here is for t-test. You see t-value? It's for the individual. Based on what you see right now, we're actually going to reject intercept model. Okay? That's what I mean. Okay, go ahead. Significant. Yeah, I'm still coming back here. When the p-value of interaction is not significant, right? It's actually it's not nullifying the idea that the full model is better. Maybe what that guy is just saying is this. Maybe what he's saying is, I'm going to show you now, is this. That is still better than the intercept model. I understand what you mean that, oh, the interaction we incorporated is not significant, but that doesn't nullify the entire model. Because what is going to give us a way, like, the most important thing that we need to pay attention to is the p-value. This is a p-value associated with the test. At times, a country could have a significant production, and one of the states or two states in that particular country may not have a significant contribution to the country. It doesn't matter. Okay? Because the country is made up of so many states, Okay, now this is the graphical way. Do you know this guy here? Okay, you're talking about intercept, okay, with and you take a look at this. This is the full model. This is the full model one. In the full model one, what do you see? You have two lines, right? Oh my God. The two line, why am I having two line? When they come together, they interact. What is this one telling us? This is telling us like that interaction effect may not be significant. Because for interaction to occur, the two lines supposed to intercept, right? Exactly. Now, I'm gonna walk you through something now. Now, I'm done with F-test. What do we use F-test to do? It's like comparing nothing with something. That is what we call F-test. Comparing nothing with something. Comparing intercept model with a full model. The full model could be simple linear regression. The full model could be multiple linear regression. The full model could be any other complicated model. Because in any other model, there's an intercept model. Does that make sense? But do you know what we want to do now? We are not, when we want to go to partial F-test that we also call nested F-test. When do we use partial F-test? Oh, we use partial F-test when I'm comparing something with something. The something here is simple and this is complicated. No intercept. Do you understand what I mean? The F-test, we use F-test when we compare an intercept model with any other form of a model, but we use partial F-test or nested F-test when we compare simple model with complicated model. The simple model is not going to be intercept. What will be the difference between the simple model and the complicated model is going to be the number of explanatory variables. Now, let's take a look at this now. Oh my God. We have a research question here. Can you look at the research question here? I said everything is going to start from a research question. Okay. The question is, does a physical attractiveness, okay, which we call Pepe as a variable here, affect the relationship between the quality rating and the easiness rating of an instructor? That's what we want to answer. I want to answer that question now. To be able to answer this question now, we're actually going to compare a simple model with a complicated model. What is the simple model here? A simple model is when I only consider, when I have a model, which is I'm only having easiness as an explanatory variable. The complicated model now, okay, the complicated model is the model with interaction that we talked about the other time. The model with interaction where we have easiness, PPS, and the interaction. And let me tell you this, before I can use this, please pay attention. Before a partial F-test or a nested F-test can be used, then the simple model must be nested in the complicated model. What do I mean by nested? Take a look at that. We can find it here. How? the way you can find it right now, you're going to see something right now. Do you know that if this guy is 0 and this guy is 0, the complicated model becomes a simple model, isn't it? That is why it's called nested. The simpler model has to be contained, okay, in a complicated model. Okay, now, and what we indicate that, what do you think we introduce? In the simple model, there is no categorical variable, right? Pepe, right? Now, and that is the reason why here I'm trying to say when Pepe yes equal to 0, please pay attention and ask me question. When Pepe yes equal to 0, in the complicated model here, okay, in the complicated model here, anywhere you see Pepe yes, if you plug in 0, it will take you back to the simple model. Do you see that? Does anybody see that? Okay. It's going to take you back to the simple model when Pepe yes. And don't forget, look at the question. Does physical attractiveness, Pepe? That is what we're testing. We are testing the effect of the categorical variable, Pepe. We already have a simple model in place initially, which is the one that talk about relationship between equality and easiness. That is already in place. We are now incorporating the effects of Pepe, and that very Pepe is categorical. Okay, when Pepe yes equal to 0, we have the intercept model. When Pepe yes equal to 1, please pay attention, mathematics now. If you go back in there, if you come in, give me 1 second, I'm going to clean up. Okay, if you come back here now, okay, I'm plugging Pepe yes to be equal to 1. Okay, anywhere you see Pepe yes, you plug in to be equal to 1, you automatically going to have a new intercept and a new slope. Do you see that? The intercept has changed and the slope has changed. Are you seeing that mathematically plugging in 1 anywhere you see Pepe yes? If you plug in 1, beta 2 times 1, beta 2, so it's just going to be beta 2 plus beta naught. The same thing. And that was why I said the 2 Pepe yes, which means you now have 2 groups. This is the first group. This is the second group. The 2 groups are based on easiness, right? The first one is you don't consider, there's nothing like Pepe, that, categorical that you introduce. But the second one, can you see that? And I say the 2 Pepe group could have different relationship. The way easiness is related to quality in the first group is different from the way easiness is related to quality in the second group. Why is it different? Because they got different intercept, they got different slopes. Does that make sense? Okay, now graphically speaking, that is a simple model. This is a complicated model. Graphically speaking, the simple model, of course, the simple model, you only have easiness, right? Okay, now take a look at this. This is what it comes to. We have a 2 competing model. The first one is the one that have easiness only. The second one is the one that have the main effect and the interaction. Okay, take a look at that. And don't forget, before using a partial F-test or nested F-test, the simple module has to be nested in the complicated. Okay, it has to be within that. Okay, now how is the hypothesis going to be? Oh my God, look at this. What do you say? Y beta 2 equal to beta 3 equal to 0. You remember that time? Okay, if you have a complicated module, let's come back here. If this guy is 0 and this guy is 0, automatically you have the non-hypothesis. Therefore, mathematically way of specifying what we are testing in terms of regression parameter should be beta 2 equal to beta 3 equal to 0. Okay, And that is why you have this guy here. Do you see that? That's a mathematical way to say it. Okay? Then the alternative is going to say at least one of that is not zero. At least one is not zero. Now, we need a test statistic value. Okay? We need a test statistic value for that. Please pay attention. This is very new. Partial F-test, okay, is different from F-test. Okay? The test statistic is going to change. Look at that. Please pay attention. We're actually going to have, because how many modules are we having? Are we comparing 2 modules? Then there will be 2 residual sum of square. Does that make sense? There will be what? 2 residual sum of square. And don't forget, residual sum of square is unexplained variation. If I really want to know how good you are, you know what I'm going to do? I will analyze your mistakes. I will analyze your unexplained. That's how to know. Okay? Now, take a look at this. The very first one, please pay attention. If you don't understand, tell me. This guy here, that is the residual sum of square of a simple module. You see S? You see subscript S? Then this, residual sum of square of a complicated module. Okay? Now, divided by 2. Why 2? We are testing 2 parameters, effect of 2 parameters, beta 2 and beta 3. Does that make sense? Now, in the denominator is residual. In the denominator, it has to be residual sum of square of complicated. Why is it n minus 4? N minus 4, 4 is the number of parameters in the complicated module. Does that make sense? So that is it. Now, if I now want to have a general formula, oh my God, that is the general formula. The residual sum squared of a simple module minus the complicated module divided by the difference between the degree of freedom for simple module and the complicated module divided by that. That is the general one. How are we going to run this in R? Please pay attention. What are we doing right now? We're actually conducting partial F-test, which we also call nested F-test. Now, let's see the ways we're going to run it in R. Oh my God. Please pay attention. Pay attention. We're actually going to run 2 modules. You see the first one? That is a complicated one. The second one, the simple one. Can you see that? You're going to run 2 modules. And if I were you, you have to give them a different name here. Look at that. You know, I say MOD. You can say MOD1, MOD2. And this is another one. Can you see a different name? Any question on these 2? You're going to run 2 modules. You know, with the F-test, do you run 2 modules? With the F-test, no, you don't run 2 modules. But with the partial F-test that we also call nested F-test, you're actually going to run 2 different separate modules. One complicated, the other one simple. Now, after you do that, then you're now going to write this. Oh my God. You're going to write ANOVA. All has to be in a lowercase. The very first module that you're going to write should be simple module. It shouldn't be. This shouldn't be other way around. I'm going to say that again. When you write ANOVA code, the very first is going to be MOD1. MOD1 is a simple module. Y followed by the complicated module. Any question on that? Let's see the output. The output is going to come out this way. Oh my God, this is the way it's going to come out. It's going to come out in this way when you run it. And I'm going to explain that to you one at a time. Pay attention. This is the output. You know what is going to be displayed in the output? The output is going to display module 1, module 2. Can you see that? It's going to remind you that your module 1 is only going to call that module 1 if you write the simple first. You got to write the simple first. Okay. Now, it's going to remind you that your module 1, you are only looking at the effect of easiness on quality. Your module 2, you are looking at the effect, the main effect of easiness, the main effect of pepper, as well as their interaction on the quality. It's going to tell you that. Please pay attention. Something is coming now. Something is coming now. Oh my God, what is this? Okay, what is that? The very first one, 364, is the degree of freedom for error for the simple model. For the complicated model, 362. And you know what? Let's look at the RSS. What is expected? RSS. The RSS here, the first one, 174.25 is a residual sum of squared for the simple model. Why this guy here is for the complicated model? Can you see that? Okay. But you know what is important to us? Okay. Okay, what is important to us? This is the F statistic value. Do you know that this is what you're gonna get when you make use of this guy here? Oh, give me 1 second. When you make use of this guy here, that's what you're gonna get. And that is what arrow is giving you automatically now. Okay, arrow is giving you automatically now. But you know what we need finally? We need a p-value. Okay, we need a p-value to take a decision now. What is happening now? The p-value is less than 0.05. Okay, in this case, we are rejecting the simpler model. Okay, we're actually saying the complicated model will do the job. Okay, now we want to have conclusion. Okay, our conclusion now, we're actually going to have two conclusions. The first one is going to be technical. The technical condition is the one that is understood by statisticians. Okay, why are you now also going to give a conclusion that's actually commensurate with its context? Let's take a look at the technical conclusion now. Oh my God, it said a small p-value leads to rejection of the non-hypothesis, which means we are rejecting the simple model. Okay, now, and that means the complicated model fits the data significantly better than the simple model. So, which now, if I'm just saying this to maybe if I'm consulted by somebody outside statistics and I'm using this terminology, it's going to be looking at me. What are you talking about? Break it down. Break it down. Now, if I want to break it down, I'm going to go back to the research question. And what I'm trying to say is that the physical attractiveness affects the relationship between, don't forget the physical attractiveness is categorical, right? Okay. The way Professor look, okay, affects the relationship between instructor quality rating and their easiness rating. Done. Period. That is the end of the research. Did you see now there's a connection between statistical conclusion and the conclusion according to the context? Is there any question for me today? This way we're going to stop. Any question? We're counting down to be time 2. Yeah, go ahead. Oh, the scatter plots. This one? No, this is when it is set. This is when it is set to 1. Let me take you back. We have when it is set to 0, which is this guy, what we're doing here. When it is set to 0 is the first one. And when it is set to 0, you know what you're trying to say? When it's set to 0, we're trying to say the first group, which is Pepper, yes, no. So when it's set to 1, you're referring to Pepper, yes, yes. That's another group. So when you take a look at this, in the 2, we have both Pepper, we have both categorical variable, but one with a lower level, one with no, the other one with yes. Yeah, yeah, yeah. In that one, the reason why we're trying to say the relationship may not be the same when we do that mathematically the other time. In fact, look at this. From the graph, the intercept is not the same. They say the intercept not the same, and that now confirm what I'm trying to talk about. Shear, you know, see this one, see the intercept here, and see see the slope. But let me tell you this: seeing it mathematically like this does not indicate that difference exists statistically, and that is the reason why, even though this graph may be giving us some information, when a doctor, when a patient visit a doctor in a clinic, if a doctor will look at the patient, the way the patient look at time will give the doctor the kind of